Yes, if we have some time, we can do a Kirchhoff's rule problem by hand. I mean, we've already done it by hand here. This is done. The only thing that you would have left to do is to solve this equation for I3, get a number, plug I3 back into one of these equations, get a number for I1 or I2, plug in I1 on I3 or I2 and I3 into one of the other equations to get the last one. I mean, it's pretty much done at this point. And if you want to go through the algebra at the end, we can do that too. But pretty much it's done at this point. It's just algebra. So yeah, we can do that after we're done. We probably will not get done with everything before 10:40 today, but we can do it afterwards if we want. So we have 40 minutes now to cover the rest of the chapter. We've gone through everything to Kirchhoff's second rule, or everything through Kirchhoff's rules, and now we're going to move on to DC voltmeters and ammeters. Now we've already used voltmeters and ammeters in the last lab that we did. We used a voltmeter and ammeter, and we used them in the electric field lab. So we kind of got a little experience with them, but we haven't really learned how they work. We learned that we're supposed to hook them up in certain ways, but we didn't learn why. But voltmeters and ammeters are used all the time. All the dials in your car, for example, every single one of those is either a voltmeter or an ammeter. The battery one is obvious. If you have a battery indicator light in your car, it's obvious that that's a voltmeter because it's measuring volts, right? But if you don't have one of those, it's not so obvious. But all the rest of these are also just voltmeters and ammeters. There's no real difference, especially in new cars, because new cars mostly have the digital odometers. Old style odometers that had the little clicking numbers that were mechanical, those are not voltmeters because they literally were just clicking a wheel as your wheels went around. But everything else in these newer cars are voltmeters or ammeters, and it's some kind of instrument that's creating a voltage or a current that's being read by these meters in your car. So voltmeters we're going to start with because they're simpler. A voltmeter just measures the voltage drop across a component in a circuit. And so if you connect a voltmeter on one side of a component and on another side of a component, you will measure the voltage drop across that component. If you measure the voltage across a resistor, then you'll know how much energy that resistor takes out of the circuit. You'll know how much energy per charge. If you knew the current, you would know all of the energy, everything you need to know about the energy. So you just connect it across different components. And you can connect it across multiple components, more than one component, to measure the voltage drop from this point of the circuit to this point in the circuit. That's perfectly fine. You can measure the voltage across the battery or whatever else. But a voltmeter just does this. And the reason it can do this is because it has an extremely high resistance. The voltmeter itself, you notice, is drawn as a circuit. It has an entrance into the voltmeter and an exit from the voltmeter, and it creates a little circuit around this resistor. But the resistance in the voltmeter is so extremely high that almost no current goes through the voltmeter. Almost nothing. Like a billionth of the current might go through it in a good voltmeter like this. A voltmeter, good digital voltmeter, there's almost no current goes through it when you're measuring the voltage. And that's important because if current goes through the voltmeter, less current is going to go through the resistor you're trying to measure the voltage across. And that will change the voltage across the resistor. So you want a really high voltage a really high resistance voltmeter that's not going to affect the circuit very much. You don't want it to change what's going on in the circuit because you want to know exactly what that voltage is. So voltmeters have high resistance, and that's what you need to know. Ammeters are exactly the opposite. An ammeter is what measures the amps, or the current, through a circuit. And in order for an ammeter to work properly, you need to actually insert the ammeter into the circuit so that all the current in the circuit goes through the ammeter, so that you can measure how much current is going through that circuit. And so if an ammeter has resistance, it's going to change the circuit because you're putting it into the circuit. You're actually making it part of the circuit. When you're putting in an ammeter, you actually have to open the circuit somewhere and insert one end of the ammeter at one end of that opening and the other end of the ammeter at the other end, so it becomes part of the circuit. So if it has any resistance at all, it's going to affect the circuit. You don't want it to affect the circuit. So an ammeter needs to have zero resistance, but that's not realistic. Nothing has zero resistance. I can't say nothing has zero resistance, but very few things have zero resistance, and those things that do have zero resistance are not easy to work with. So we don't have ammeters that have zero resistance. We have ammeters that have very, very low resistance. And if their resistance is very low compared to the resistance of the circuit, then it shouldn't matter that much. So most ammeters have a resistance in the very low ohm or fraction of an ohm range, which is ideal. You want to have a very low resistance, so when you put it in there, the circuit doesn't really change much, and you can measure the actual current going through the circuit. Now, there is a difference between the types of meters. There are galvanometers, and they don't have a really good picture of a galvanometer here. There are analog meters, and there are digital meters. Now, let me get my demonstration galvanometer really quick, and so you can see what it looks like. This is a huge galvanometer, and that's because it is made for demonstration purposes. And let me, I'm going to put this is going to be a weird way to do this, but so that it shows up on the video that we're making, we're going to do this a weird way. I'm going to put this right here. What did it just fall out? On the motor. I made that when I was a student. And then I'm going to point my camera at it. Let's see if I can do this. Yes. So here is my galvanometer. I'm going to point my screen camera at it so you can see it here. And what we're looking at here is and it's backwards on my computer. Sorry about that. I don't know if I can change the backwardsness. But anyway, what we're looking at here is the scale, first of all. And it's got this needle on it. And you can see that it says galvanometer volt-ammeter. So it can either be a voltmeter or an ammeter, depending on how you set it up. On the back of this are a series of resistors, and what we will call resistors and shunts. These are the shunts, which are really low resistance resistors, and these are the resistors, which are high resistance resistors. So if you want to make this into a voltmeter, you use these high resistance resistors and you plug them in the front into this little clip right here. But if you want it to be an ammeter, you use these really low resistance shunts and you plug them into these plugs up here. But what is the idea? The idea is that current will come in, if we're using it as a current meter, we'll connect it into the current side, which is going to be over here. And current will come into the ammeter, and it will go through this tiny little thing down here. You can see it's essentially a coil of copper wire, and the current goes through that coil, and the copper wire, and this is inside of a magnetic field, so it actually creates a deflection. We'll learn more about this in chapters to come. But it creates a magnetic field that causes this needle to move one way or the other, depending on the direction of the current. And the more that it moves means it has more current. And it's essentially, the reason it's analog is because it's analogous. The magnetic field that moves the meter is analogous to the amount of current that goes through it. So more current, more field. And that's what we call an analog meter. So if I have a very low resistance shunt in here, more current, more field, you're good to go. But if I use this as a voltmeter and I put the big resistor in here, then I connect over on this side to my leads that I'm going to test things with. I'm going to Then I'm going to put these leads on either side of a resistor to test its voltage, to measure the voltage across that resistor. If that is the case, then I get a very little amount of current through here. But because the way it's set up, that little amount of current can also deflect this thing. So it's an indirect deflection because of the high voltage in here, or the high resistance in here. But I still get a deflection, and it will tell me the voltage. And it's set up to measure either voltage or current depending on how I use it. So this is an analog galvanometer, they call it, named after a scientist once again. And these things are actually still they're used quite a bit still today because they react very quickly to the current and the voltage put in them. So if somebody is looking at a voltage that's changing very rapidly, or that they need to see a quick voltage really quickly, or whatever, then they still use these analog galvanometers, and they can get very expensive. The really nice ones can be $5,000, $10,000. Hello. Then we have our digital voltmeter, right? And a digital, this is called a digital multimeter because it does many things. It can be set up so you can change it here to measure AC voltage, so that's alternating current voltage, or you can turn it over here to DC voltage to measure direct current voltage, or you can choose to measure your current down here. All the way down here you can choose 20 amps of current, so up to 20 amps, or below into the milliamp range, or into the microamp range. It's actually really easy to measure small currents, and so lots of multimeters can measure microamps or even nanoamps. So it's pretty nice. But this one also measures. It can use a device to measure temperature or resistors, and even capacitors, or even frequency. That's kind of a cool feature. It can measure frequency, and it can measure. What else can it measure? Oh, you can actually test little microchips in here and other things. It's a pretty nice multimeter, and it's set up that way. But it's still the same thing. On all these meters, you always have, when you're measuring voltage, you have to plug it into a different place than when you're measuring current. In this one, when you're measuring voltage, you plug it in over here. There's a ground right here, which is called the common, and then there's the voltage side right here. So you plug into ground and voltage to measure voltage. But when you're measuring current, you have to choose one of these other holes. For 20 amps, you use this big one. For the smaller currents, you use this smaller one. And it's always this way because on the current side, you want a very low resistance. So this side is set up with low resistance. This side is set up with high resistance. And it really matters because if you have it plugged in incorrectly, if you're plugging in the current side and you measure voltage, you're measuring voltage with a really low resistance, you can sometimes get a huge current through that side and blow out the current side. So you got to remember to plug it in the right side so you don't blow up the multimeter. Now, I was once working in a laboratory next to another laboratory, and in the laboratory next to ours, the professor was trying to measure an extremely high voltage using one of these cheap multimeters like this. To measure high voltage, you're supposed to use really high quality voltmeters that are designed for that. But he was measuring it just with this little cheap thing, and he was trying to get around it, trying not to waste money. And he had hung the multimeter up from the ceiling so that they wouldn't have to be touching it if it exploded. And I was sitting there working, and I hear this boom, and this voltage had been too much for the multimeter. The voltage was so high that it drove a current even through the high resistance of the voltmeter, and that current was pretty high, and it literally exploded the thing. When I went over there to see if he was okay, this thing was hanging in pieces from the ceiling, and it was smoking, and it was pretty funny. But so be careful measuring things with voltmeters is the bottom line. All right, so galvanometers, voltmeters. Taking measurements alters, changes the circuit. We talked about all that stuff. Let's move on and learn. This one talks about measuring voltages again. Here they're using a potentiometer to change a voltage. We learned that a little bit in our lab. So here's where we need to end up. We need to finish up here. So, this section on null measurements is a section that talks about devices that are used to measure things indirectly. And especially when you're measuring voltages, it's very difficult to measure very low voltages, very small voltages. But it's not all that hard to do them indirectly if you use correct technique and the correct instrumentation. So one of these instruments that we can use is a potentiometer, which is the variable resistor. And when would we use it? Well, we would use it to measure a very, very small resistance, for example. If you have a very, very small resistor in your circuit, but you can't measure it because it is so small, then you can use one of these devices, these potentiometers, to measure that small resistance with a voltmeter and with some other devices. And the way to do it is to set up a circuit called a Wheatstone bridge. And the idea is actually right here. Here is the Wheatstone bridge. The Wheatstone bridge is essentially two paths of resistance. You have your battery down here, your power supply down here, and the current is going around and around. As it gets to this branch, the current takes two paths. One path along the top side, one path along the bottom side, and then it recombines to take one path again back around through the circuit. The idea here is to measure a resistor that goes between the two paths, resistance G, and you put a little, let's see here. No, sorry, that's not the idea. This is a different setup than I was thinking. The idea is to put your galvanometer in between here. So this galvanometer is designed to measure a current that's going between these 2 points. Now, if the point B and point D have exactly the same voltage, there will be no current. Absolutely no current through here. In order for point B and point D to have exactly the same current, you have to have equal resistance for R3 and Rx compared to R1 and R2. So if R1 is twice as big as R2, then R3 would have to be twice as big as Rx in order for there to be no current passing between here. So what they do is they connect this up, and then they flip this switch and they see if there's any current flowing. If there's any current flowing, they start adjusting resistor 3 until there's no current flowing. And then they can actually measure resistor 3 to figure out what resistor X is supposed to be, because if R1 is 4 times as big as R2 and R3, then R3 has to be 4 times as big as Rx. And they can measure resistance 3 to do that, to figure out what Rx is. So Rx is your very, very small resistor, and you use the Wheatstone bridge to measure it. They actually give here's the equation for this. The equation for Rx is R3 times R2 over R1. So you take this R2 divided by R1 ratio, multiply it by R3, whatever R3 is, and that will give you Rx. So this is the only equation you really need to know for this Wheatstone bridge. And I did give you a Wheatstone bridge problem in the homework. So this is the equation you need to know for that. Okay, the last thing of this chapter is what we call RC circuits, resistor capacitor circuits. And this is a big deal, and it's quite interesting actually. What is an RC circuit? Well, let's take a look. An RC circuit is a circuit that looks just like this. It has a resistor, and a capacitor, and a power source, and they usually put a switch in it too, just to make sure that we know what's going on. Okay? Now, let's take a look at what it does. I don't know if they have one here. Doesn't look like they have one, so let's go look one up. Okay, let's get rid of, we don't want that one. Here we go, that's a good one, I think. Let's see if this one works. That doesn't work. Okay, let's try again. We need to find a demonstration of how this works because it's much easier to see this in demonstration. That's YouTube. We want actual interactive one. Let's see here. It's not right. Let's try this one. Maybe this one has it. Let's use this one. This one's actually a really good one. So this is a site made by the University of Colorado several years ago, and let's see, physics, and they made this great app where you could make your own circuits. Let's see if we can find it. It's conductivity. Where is it? Come on now, capacitor. Here it is, circuit construction. There we go. Okay. So let's use this. Should probably just download it. I did download it. Good for me. Okay, come on now. Okay, so what this does allows us to build our own circuit. We can start with a wire, and the thing that we're being shown here is the wire itself, but also the movement, the charges inside the wire. Right now the charges aren't moving because there's nothing to make them move. You have to have some kind of voltage to push the charges around. And so we just have a wire to start with. We're going to add in some things. Let's add in, it's not giving me, what's in the grab bag. I want a capacitor. Where's my capacitor? Let's see. Electrons. It doesn't have any capacitors. Dang it. Let's switch to the different one. Maybe the other one has capacitors in it. Yeah, this one has capacitors in it. Let's use this one. Okay. Open, open, open. Okay, so now we have capacitors. Let's grab a wire. We'll put in a wire here. We'll grab a capacitor. We'll connect in a capacitor. We'll put in a resistor as well. Put in a resistor here, and we'll turn the resistor down so we can make our circuit. And then we'll put in a battery. And then the last thing I'm going to put in is a switch. And then I'm going to put in a wire right here. Connects. Well, I'm going to put in two wires so I have some. Actually, I'm going to put in a. Let's delete that. Remove. Then I'm going to put in a light bulb. Put a light bulb in right here somewhere. And then I'll put another wire right here. Okay, so Notice that nothing's moving right now because the switch is open. If I close the switch, look what happens. The light bulb, you can almost see it light up there. We need some more battery. Let's get some more battery in here. I'm going to disconnect this, split the junction, and I'll put in a few more batteries. We need some more voltage. Maybe I'll burn out my light bulb. Let's turn this one. Turn this one too. Okay, let's just make this one longer. There we go. Okay, so now, if I flip my switch, let's see what happens. Okay, nothing's going. Why not? It's not too much voltage, actually. Look at the capacitor. Can current flow through a capacitor? It only stores the charge. And when I first turned it on, did current flow? We had a little bit of flow, but then what happened? The current flowed to the capacitor, filled up the capacitor, and now it's full. Can't do anything else now, can I? Now that the capacitor's full, I can't do anything. I'm stuck. So what I do here is I can split this junction, take out this capacitor. Actually, I can do this easier. I can actually click on this and I can discharge the capacitor. So I'm going to take all the capacitors off of it, all the charge off of it. So I don't have any charge on it. I'm going to go ahead and connect this capacitor again. So now it's connected again. And let's see what happens. Turn it on. Oops. Am I connected? I'm connected, okay. And let's change the capacitor. Let's make it higher capacitance too, done. And let's reset everything. Oops, it's not what I wanted to do. I wanted to reset the dynamics. Dang it, now I gotta start again. I hate that. Maybe I can undo it. Nope. Got the resistor, wire, battery, battery. Make sure I have them all pointing the same direction so they don't fight against each other. Put in a light bulb here. Put in another wire here. And I'll put in a capacitor up here. And right there. So now, good. Connect. So now it's going. I turned it on. And it goes and goes and goes, and the light's on, and then the light dims out as the current stops because I've charged the capacitor. Right? Capacitor's charged now. Let's see if I can adjust this somehow. Apparently I can't. That's okay. So now it's completely done. Now let's reset the dynamics, and it does it again. Oh, I know what I'm missing. I'm missing my switch. Let's split the junction here. Let's put in a switch. There we go. So now let's reset my dynamics. It's like nothing happened, and I'm going to turn on my switch. And it starts out, the current starts out going really great because there's no charge on the capacitor, and charges can run towards that capacitor as fast as they want. But as soon as charges start building up on that capacitor, they start resisting the current. They start pushing back against any other charges that go there. And eventually the charges stop going to the capacitor because it's full, right? So it starts out really bright, the light bulb, and then it goes dim, 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 dim. In other words, the current starts out really high, and then it dies off as the capacitor fills up, right? And it depends on the capacitance. The capacitance determines, in part, why or how fast this happens. So let's change the value of the capacitor. Right now it's 0.10 farads. I'm going to change the capacitance to 0.2. Let's see what happens. So instead of 0.1, it's 0.2. I've changed it. I'm going to reset the dynamics. What happens? Does it take longer or less time for the charge to slow down? It's longer because there's more space on the capacitor for that charge to go to. So it takes longer for the capacitor to fill up, right? So it takes longer. What about the resistor? If I change the resistor, if I change, right now the resistance is at 10 ohms, let's change it to 100 ohms. And let's see what happens. Reset dynamics, and let's go. What's happening with a bigger resistor? Let me undo my switch here. So if I start it, what happens if I make a bigger resistor? Everything happens slower, doesn't it? The light never gets very bright. The charges don't move very fast. So changing the resistance changes the amount of current that it starts with. It's still going, but it's going very slowly. Okay? It's going to take forever for it to happen, and it didn't start out very bright. So the resistance determines the original current. That changes the maximum amount of current. It doesn't really change the time that it takes. It just changes the original amount of current. It's not actually true that it doesn't change the amount of time. It doesn't by itself, but together with the capacitance it does. So they both affect things. Both the capacitance and the resistor affect things. And it turns out that we know how it works. So here is that's not a very good. Here we go. That's not right. Let's see here. They don't show the current for this, but they should. This shows what if you start up this circuit that we were just playing with. We just flipped the switch. This shows you the voltage across the capacitor, and we can see that happen too. Let's go back to our applet here. Where is it? If we want to see the voltage across this capacitor, we can put in a voltmeter, and let's see if here's a voltmeter. So we'll put in a voltmeter right here across this capacitor and measure the voltage here and here. And right now it's showing as negative 30 volts, and it's slowly changing. But let's start again and let's see what happens. It starts off at 0, and it goes up and up and up and up to it goes down and down and down to a negative. If I change these around here, it'll be positive. So it goes up and up and up and up, and it eventually gets to a high voltage over time. It takes some time to get there, but it does do it. If I change this resistance again to a lower resistance, it will happen quicker. So reset our dynamics. See that it starts at 0 and it goes up to a high voltage. Eventually it gets to a voltage that it's just going to kind of stay at. So let's see where that is. It gets up here and it's slowing down. The change in voltage is slowing down, slowing down, slowing down, slowing down, slowing down. It's changing less and less and less and less as we go up. And eventually it'll reach a peak voltage that it won't go any higher. I wish it would do it a lot faster than it is. Good night. Let's change our capacitance too. And let's reset dynamics. So you can see that it slows down, slows down, slows down, and eventually it's going to reach a place where it's just not going to increase at all. It's just going to kind of sit at a number and not change hardly at all. And it takes a little time to get there. Looks like it's going to be about 36. Looks like each of these volts is probably about 9-volt batteries. So the maximum is about 36, and it's never really going to get there. It's just going to slow down more and more and more and more until it just barely almost gets to 36, right? And that's what we see here in the chart here. That voltage increases, 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 and gets to the highest voltage that is being supplied to the capacitor, which is the voltage of the batteries. Okay? The time that it takes to do this, of course, is difficult to measure because it never really gets to that 36. Never quite gets there. So what we do is we measure the time that it takes to get to 0.632 times that voltage. Now, why 0.632? It's a mathematical thing. It has to do with exponential functions. But the time that it takes to get to this fraction of that maximum voltage is what we're going to call the time constant of the circuit. And the time constant of the circuit happens to be part of the equation for this, which is that the voltage is equal to the maximum EMF times 1 minus E, which is the natural number, to the negative T over RC, where RC is the time constant. Resistance times capacitance is the time constant. So it's actually both resistor and capacitor combined together, multiplied together, that determines how fast these capacitors charge up. It's a combination of the two. This equation turns out to be quite important. This is the charging equation for a capacitor when it's connected with a resistor. If it's connected with a resistor and you're discharging the capacitor, it's a different thing. So let's go back to our applet and take a look. So here's our applet. We're all done. I'm going to disconnect my switch here. So my switch is completely disconnected. And what I'm going to do is I'm going to take this capacitor and I'm going to disconnect it. I'm going to disconnect it, maybe. Split the junction on both ends. And notice that my capacitor is still charged. So I'm going to take it out here and I'm going to flip it around. So it's pointing the other direction. And I'm going to connect it again back into here. Notice that nothing can happen because there's no circuit. It's not connected. So now I'm going to connect it again into here, if I can. Whoa, what happened? There we go. Come on, connect. Ah! It's driving me crazy. There we go. Now it's connected. Okay, that's all connected again. Notice that nothing's happening because the circuit's not closed. But there's another thing that I need to do. I'm going to try to discharge this capacitor, but I don't want to have any batteries in here. So I'm just going to remove the batteries, because I don't need batteries to discharge the capacitor. I just need a connection. So I'm just going to connect this wire to this light bulb over here. And so now if I close this switch, there's already charge in the capacitor. It's charged up and it wants to whatever. It wants to discharge. So I'm going to go ahead and close it and see what happens. Ah, what happened? Am I connected? I'm connected to the wrong thing, I think. Why won't it do this for me? It should. Oh, I'm still not connected. That's my problem. It's not, the resistor is connected to the wrong side. I want to now connect this guy. There we go. So that's connected. Now I want to connect these two. Let's see what happens. Come on. Give me a break. Make a wire. There we go. So now when I connect it, there's no batteries, but the charge flows from one side of the capacitor around to the other side, and it discharges this, right? Let's reset the dynamics. Oops. Let's charge this capacitor. Let's actually disconnect the circuit. We'll charge the capacitor. Let's see. Can't charge the capacitor. Dang it. That's annoying. I want to charge the capacitor. To go back to my batteries. Anyway, if we'd shown the voltage, we would have shown it as starting out at a high voltage and then immediately discharging very quickly and then slowing down as it gets towards zero. That's what I was trying to show you, but it wasn't obvious. But anyway, here what happens is the voltage drops really fast at first and then it discharges slowly. And this is the equation for the discharging capacitor. Again, there's a time constant, R times C, to which that's what it takes for 62% of the charge to go away. So this is an RC circuit, and it is the beginning of advanced circuitry. This is where the circuits, the difference between just a resistor and a battery are connected, and your cell phone. Your cell phone has all kinds of resistor capacitor circuits in it. It's pretty much the whole cell phone. Resistor capacitor circuits, lots and lots of them. It's what makes a cell phone possible. So it's the difference between simple circuits and circuits that actually do something interesting. So let's take a look at this example right here really quick. One thing that you can do with a resistor capacitor circuit is you can design something that flashes, because you can charge up the circuit, and then when you can charge up the capacitor, when the capacitor is charged, you can flip a switch to another circuit and use that charge to make something flash, like strobe lights or return signals or something else like that. And so in this case, we have somebody who's trying to use a strobe light to capture a picture, to make a picture of something that's moving at 5 times 10 to the 2 meters per second. So they need let's see, they've got the duration of the flash has to be related to the RC time constant. So the apple has a sphere of a diameter of 8 times 10 to the minus 2 meters. That means that the bullet, as it moves across this thing, is going to move across it in a certain amount of time, and we want to capture that. So how long does it take the bullet to go across the apple? It's moving at 500 meters per second. The apple is 8 centimeters across. 8 centimeters? That's pretty big apple. But that's not that big, I guess. So we calculate the time by taking the length of the apple divided by the speed of the bullet. So this is the amount of time that we want for our time constant. 1.6 times 10 to the minus 4 seconds. Now they've told us the resistance of the circuit. It's 10 ohms. We need to calculate the capacitance in the circuit from the time. So we rearrange the time constant equation. Time is equal to R times C. We rearrange it to be C equals time divided by R. We take the time that we calculated, 1.6 times 10 to the minus 4 seconds, which is a tenth of a millisecond, and we divide it by the 10 ohms, we get 16 microfarads. So that's the capacitor that you need to make a flash that's going to flash that quickly. Plain and simple. So if you charge up the capacitor and then you connect it to the flash, most of the light that's going to come out of the flash is going to come out in that time right there. All the current that comes out is going to come out in that amount of time, most of it, 60% of it. And then you'll be able to shoot your bullet and flash your camera, and it will take a picture of that camera going through the apple, or that bullet going through the apple, rather. And that's exactly how pictures like this are taken. That's exactly how this picture was taken. It's in a dark room. It's completely dark. They put a gun right over here. They put the gun at a specific distance because they know how fast the bullet is traveling, and they know how fast the time constant is, right? So then as soon as they fire the bullet, there's a microphone in the room, or an electric thing in the room, depending on how they do it, that senses that the bullet has been fired. So at the same time the bullet is fired, there's an electrical impulse that goes to the circuit. The electrical impulse that goes to the circuit flips the switch and discharges the capacitor through the flash. And then the flash goes off in the dark room, and the only thing that the camera catches, and the camera is on the whole time. The camera's aperture is open the whole time. So it's just taking a picture of the dark room to start. And then the flash goes off and it takes a picture right as the bullet's going through. And if you time it just right, you can have it as the bullet is inside the apple, as it's coming out of the apple, before the apple. So you can adjust your timing to take pictures at different times during the action. But that's what happens. That's how they take those pictures. Here's one at a different time. The bullet is still in the apple, apparently. That's kind of crazy. Here's one where it's shooting some stuff out the top of the apple. So, anyway, that is what we call the time constant of an RC circuit. And that is everything we're doing. So, have a good weekend. Homework is posted.
Do you have any office hours tomorrow for a few questions?
I do have office hours on Fridays. They are at noon, I think. From noon to 1. And I can be here in the morning if you want.
That's not bad. Most of
From noon to 1, I'm definitely around. Did you want to work on this algebra or do you want to do that another time?
do you think we could,
Sure. Yeah, absolutely. Is that what you want to do too? Okay. So we've got to this point where we have an expression for I1 and I2, right? We put them in over here. Let's do this a little bit cleaner over here. Who wants to do it? I'll go over it, since it's my name. I'm kind of messy. So this is my I1, 6.25, I3, minus 21, all over minus 20.65. And we're gonna have, I'm gonna add, well, let's see, we subtract, right? Subtract negative 6.25, I3, plus 15, over negative 9.25. Now there's a lot of negatives in here, so I'm going to take care of those first, right? Take care of all my negatives first. So if I have a positive and a negative over a negative, so this negative is going to turn this into a negative and this into a positive, correct? So I'm just going to rearrange some things so it makes things a little easier. I'm going to put my positive first just to make it a little clearer. So the top one is 21 minus 6.25 times I3 over 20.65. That just makes things a little cleaner. Over here, I have a negative and a positive over a negative, so that if I get rid of this one, it makes this one a positive and this one a negative, right? So this becomes minus 6.25 I3 minus 15 over 9.25. And I just like to do that because I don't like to have negative negatives in a lot of places. It can confuse people. So now I have two fractions to mess with, and they're messy because the denominators are different and everything else. But I'm just going to do this in the simplest way possible. The simplest way possible is to find the common denominator by multiplying this one here by 9.25 on the top and the bottom, this one by 20.65 on the top and bottom, or I can multiply the whole equation by both of these numbers. I'm going to do that, okay? So if I multiply the whole equation, left side and right side, by these two numbers, I get an I3 on the left side that's multiplied by 20.65 and also by 9.25. Because I multiply the entire equation by this thing, right? And then both of these get multiplied by both of these numbers, right? So I have 21 minus 6.25 I3, and this is going to be multiplied by 20.65, which is just going to cancel that out, right? So I'm going to not have anything left, but it's also going to be multiplied by 9.25. So that's what I'm left with. Does that make sense?
Yeah.
That makes sense to you? I multiplied by both of these numbers on just this, and it canceled out this one that's in the denominator and left me with that one. Now on the other one, it's going to be minus 6.25 I3 minus 15, right, like that. Positive 6.25 minus 15. And it's over 9.25 to start, but I'm multiplying by both of these, so the 9.25 cancels out. And I'm left with a 20.65 multiplied over there, right? Now I have no more fractions, which is nice. But I do have a lot of messy numbers. But messy numbers are just messy numbers. From here, I can just solve for I3. This is going to give me some number times I3. I don't know what this 20 times 9 is, what, about 180? So it's about 180 I3. I'm just going to estimate the numbers here. About 180 I3 equals, and over here I'm going to get 20 times 9 again, which is about 180. So I have about 180 right there. But I have minus 6 times 9. Minus 6 times 9 is about 54, right? So minus 54 I3. Right? Over here I have minus 6 times 20, so that's going to be minus 120 I3. And then over here I also have a minus times a minus, which is a positive, so that's 15 times 20, which is going to be plus 300. right? So then I subtract both, I get all the I3s on one side and all the numbers on the other side. So I'm going to add 54 and 120 to this side. 180 I3 plus 54 I3 plus 120 I3. And then I'm going to add 180 plus 300, which is 480. Right? On this side over here, I'm going to get 354 equals 480. 354 I3 equals 480. And then I divide both sides by 354 to get I3.
Okay.
Once I've got I3, I take it up here and I put it in this equation. A number. And I solve I2. Once I've got I2, I take I2 and I3 and I put them in this equation, or I take I3 and put it in this equation and solve for I1.
Okay, that makes sense. I just wasn't sure how you would go about from this step.
Yeah, that's all just getting rid of, and I always do it this way, I just get rid of the fractions. Because it's much easier to get rid of fractions than to try to find common denominators and all that stuff.
Okay.
So just multiply both sides of the equation by every denominator and eliminate them.
Just some positive about these two things. This here, why are we subtracting this?
Because originally the equation is this. And I solved it for I3 to get I3 equals I1 on one side too.
Okay. Okay. And plugging, what would we be plugging in for I2?
So what we did is we solved this equation right here for I1, and this equation for I2. So that we have I1 equals this from this equation, I2 equals this from this equation.
Okay.
And then we plugged these into this one.
And then from that we figured out I3 was.
Then we, yeah,
Just
right.
plugged it into these.
That's correct.
Okay, I just want to be.
And in fact, that is a really good way to do it. If you get I3 here, you can plug it into either one of these and get it as well. You don't have to plug it in up here because you've already solved for I1 and I2 here. So,
Okay.
yeah,
I think
okay. Make sense? Any questions? You good?
Thank you.
But again, I don't mind if you use Wolfram Alpha.
Yeah,
This is painful.
I just want to be
There's-
sure I have to do it.
Yeah, there's so many ways you can make mistakes here. So I don't mind if you use Wolfram Alpha for this, not a big deal. As long as you understand the basics of how to, remember the basics of how to do multivariable algebra. So that's my motto right now when I was in college. I won a prize for that.
I have a question. I need to make. You have a pencil in it.
Yeah, we were given certain materials, and a pencil was one of the materials. So.
I need to make up the lab from yesterday.
Yes.
Can I do that?
So he also needs to make up that lab,
Okay.
and he's going to make it up next Wednesday after lab. Are you available after lab next Wednesday?
Yes.
Okay.
So I have one other class on Wednesday. That's from.
That's the one that goes in the middle of that.
Yeah.
Yeah. So why don't we just have it both after lab next Wednesday, make up that lab.
Okay.
Okay?
And then I still have the first lab that needs to. I have to finish it. I think we all have to finish
If you didn't quite finish it, just turn it in.
it. Okay.
You know, finishing the lab is not as important as participating in learning things in the lab. So
Okay.
it's, you know, the speed of which you do the work is not that important to me. So if you don't quite get it all done, just turn it in. I'll mark it down for you.
Okay.
All right?
So we'll do yesterday's lab.
Yes.
Okay.
All right.
Sounds good.
Sounds good. Have a good weekend. Had a student that came in here ready to go.
And how would you recommend studying for the exam?
Study the homework, because the exam problems come directly off the homework.
So with the couple ones that I was unable to solve, I should bring them in and go over them again?
Yeah, absolutely. Yeah, the homework, the exam problems will come directly off the homework, so you'll have seen them before. What are we doing in this class today? What did we just finish studying yesterday? Trying to remember.
Measurements of heat. So
Oh, right, heat.
I didn't get my homework completed, so I said go to west to extend. I don't know.
I think I emailed back. I think I extended. Unless you just sent it. Pass it out.
Well, it was last night, and I worked for until evenings, so I was off work this morning. So I don't know.
I wonder.
I'll see you tomorrow. I'm gonna come in during office hours and go over those
Okay.
questions.
One, two. Oh, I can't remember what lab I'm doing. Anything going on, sir?
Same prices. About. Well, not the same stuff, but the same. Yeah, that same stuff. Last one, like two. I have a learning that was number.
Yes, sir. Yeah. Monday? I don't think it snows in this area.
Like, first thing.
I can't grow a mustache. Yes, that's true. I brought my pencil today. I feel like minimal. Good. How fast were you going?
70 and 40.
Jesus.
But I talked about weighing down because I have to be on
Or you did
the top of my dad said when I see one I can my knee hurts far on me.
Could have been a lot more.
Yeah. I'm pretty good at talking to cops. Pretty like actually treat the cop like a person. Maybe somebody like
All right, just the three of you so far? Okay, so I'm talking to the students in the crib and trying to make sure we're doing the same lab today. And apparently we're not. So we've got to figure that out. Where is how? Can't find a copy of that. Okay. Shoot.